Hyderabad, and Inventory S Research Company in Mumbai. Sir has 10 publications in international journals, more than 25 publications in national and international conferences, and over 30 years experience in the field of DSP, radio wave frequency, and microwave engineering. We are very honored, sir, to have you with us for the session. Thank you once again for accepting to. We're very honored, sir, to have you for the session, and we would like you to take over the session.
Thank you very much. Good morning to you all. I am very thankful to St. John College to give this opportunity, and thank you to you all on Sunday. You come and spare some time. Okay. Today, we are going to talk about Terahertz technology. Now, this technology is relatively new in all over the world also, and in India, there are very less real institutes who are doing real hardware work, because there are some reasons, technological innovations and the cost, that we will see along this presentation. And there are some very interesting applications. Next slide, please. Next slide, please. Hello. Yeah. So Terahertz technology is also known as sometimes sub-millimeter waves, because millimeter wave is a wavelength when the electromagnetic wavelength is of the order of few millimeters. Terahertz is lesser than that. That's why sub-millimeter wave. It is also called tremendously high frequency. So it is like ultra high frequency, severely high frequency. In that line, Terahertz comes in the severely high, UHF, SHF, and like that. It is also known as T-rays, T-waves, T-light, and all this mean the same thing. Now, Terahertz technology is the band of electromagnetic waves where it is up to 3.3 to 20 terahertz. Some people refer terahertz as 0.1 to 10 terahertz, but around that band. So 0.1 is 100 gigahertz and 10 terahertz is equal to 10,000 gigahertz. So at 100 gigahertz, you have a wavelength of the order of 1 millimeter, 0.3 millimeters. So you are talking about the wavelengths of the order of 300 micrometers and below. Next slide, please. So we are looking at the electromagnetic spectrum, where we see on our left side, there are low frequency components, low frequencies, and I have highlighted the terahertz part. So we can see various applications, right from radio waves to microwaves and other area. And at terahertz part, there are very few applications. I have shown some body image and all. We will see into that. But in the world, there are very few gadgets operating in the terahertz region, and there are reasons for it, because there is a technological difficulty, and that aspects we will see. And recently, people have started coming up with various devices, and it will have various applications. So we are in the band which is higher than microwave and millimeter wave, and but lesser than the in the frequency, lesser than the infrared waves. So next slide, please. Yeah. So this is another representation. So where you have microwave and terahertz falls in between, and there are some blue images which are relating to the application, where you are knowing the taxonomy of the agro products and some molecular structures and all. So that we will subsequently see. And on the right, we will see infrared and then optical band and the higher frequency. So it is another illustration. Next slide, please. Yeah, so this we have already seen. Please, next slide, please. Please repeat. Yeah, so in terahertz, now we will see the upper graph shows that terahertz is occurring naturally. See, we have not made it. We are just trying to explore where terahertz appears naturally. So upper graph shows the temperature and the natural radiation of the stars. So we all know our sun is at 5,800 degrees of surface temperature, and it has got a yellow as a main central light. And similarly, as you go on lowering the temperatures, so that as the graph is showing, so the spectral band is 3000 K, you will see predominantly green. 300 K will be, actually it is shown, it is not blue, but it is the just reddish color, and so on. And then as you go lower in the temperature, you have the radiations. So at about 30K, we see the peak of at terahertz, 10 terahertz to 0.1 terahertz. So when the temperature of the cosmos or any area is about 30 Kelvin, that is 30K, you get a terahertz radiation. So in our normal Earth surface is at higher radiation, but there are particles which are just outside the space, which the temperature is around that, and that time it is available in the space, and that radiation is getting to the Earth as your ultraviolet and other radiations are coming. But we know our ozone layer protects ultraviolet and other radiation, but terahertz comes down to the Earth. So you have a natural illumination of terahertz on the surface of Earth. The lower part is showing the loss, but unfortunately, this terahertz band is very lossy band. So as we see, because of our water molecules and the air molecules, they absorb terahertz. So we can see the upper band, in the terahertz band, you will see very high peaks. And due to the various molecules like oxygen, O2, H2, H2O, there are many peaks are available. So these are the molecules available in the atmosphere. They are responsible for the loss. And you will see on your y-axis, there are 80 dB and 90 dB, 100 dB, that kind of losses are there. So though terahertz is present, it has loss as it propagates is very high. So that is difficulty number one. Next slide, please. So there are some positives. So why, if it is too difficult, why we should go for terrace technology if it is lossy? So positives are there. It is not harmful for human body as it is a non-ionizing radiation. Now we'll have a quick look at the ionizing and non-ionizing radiation. Your X-rays, gamma rays are ionizing radiation, higher than ultraviolet light. But why? Because these radiations have got energy to knock out electrons from the atom or molecule. So why the energy of an electromagnetic wave is called a photon energy, and it can be computed by Planck's constant, that is h nu, that is h into the frequency. So at ultraviolet and higher frequency, this energy is sufficient, approximately 12 electron volts, which knock down the electron. So as a result, it can make a molecular changes. So we all know that this gamma rays and higher ultraviolet ray is harmful to the cancer, then harmful to the human skin, and it can cause cancer. Or in other, you start looking old, there are wrinkles and also on. So these higher education, higher frequencies being ionizing radiation has got a direct effect. This being a non-ionizing radiation, it doesn't harm. Now we will see that there are medical applications. That's why this point is being discussed. Now it is also transparent to many objects which are non-metal and other things. So nice that he had changed the slide. So it is going to the you can see some objects which are otherwise not visible. For example, we all know that X-ray you can see something inside, but if it is non-metal or if it is a transparent, you cannot see. So we are now this slide is showing an example. This is the commercially available camera from company called INO Canada. So it is IRX, some that is a part number, and terahertz 384. So THZ 384 is actually 384 gigahertz, but that's a little unimportant. On the right side, you see one enclosed thing, and it shows the terahertz image and actually visible image. So now you see that packet had wire rings and some other objects, which are seen as a terahertz. So in X-ray image, you will see the wire ring, but other objects, PCBs and all may not be seen, which is seen by terahertz. And the lower side, we see a plastic knife, a plastic handle and all. So many times the plastic part is not seen by the X-rays, but terahertz you can see. So terahertz can see some plastic objects. Terahertz can also see some explosives and all. So these are very interesting applications. That's why the terahertz band is getting renewed interest, and therefore the people are going after terahertz band. Now we will see the technological part. Next slide, please. Yeah, so terahertz generation, there are okay, so no, these slides actually shows one example of terahertz generation. Terahertz cannot be generated as the other electronic waves are generating, because in your RF and microwave, you simply make an oscillator and it oscillates at that particular desired frequency. This is not possible for terahertz. So that we will see ahead. But this one illustration shows that if there are two laser waves, laser is in actually infrared band, which is 1500 nanometer or some lasers, you can generate lasers at the desired frequency depending on the their atomic structures and other actually crystal morphology. And from that, if I make two lasers with a very near frequency, you can get a get a radiation of different frequency, and that you can adjust it to terahertz. So what happens? This laser pointer, they are pointing on some object which is shown in the blue dot, and that object will radiate terahertz. That is shown with the blue wave, and there is a box which is having an explosive. So it can reflect from the explosive when it detects explosive. So suppose some person is taking a bag or a suitcase, and in which explosive are there, or even a bodily they are carrying explosives. So it is very, very important application where you can see the terahertz explosives. So this is a one this dinitrotoluene, that is 4A-DNT. It is showing some peak at about 1.2 terahertz. So if you are having that frequency, you will get a very good reflection on that. There is no other way other than body frisking and actually finding the object of finding the explosive. So it has got a very interesting security applications. So next slide, please. So these are the graphs at the terahertz frequencies. So that actually people talk about at that frequency, people talk the language of which is used in optics. In optics, we generally talk of the wavelength. So on the x-axis bottom side, we are talking about wave number. That is so many wavelengths per centimeter. So that is a lingo, like language. But on the upper side, I have given terahertz. So 0.6 terahertz, yes.
Sir, just a second. I think there is some audio issue. Just give me a minute.
Please look in.
Sir, can you speak? Or guys, please write in the comment section if you are able to hear us. Just write in the comment section or give a thumbs up. It's fine for us. We can understand. Is the audio fine? Okay, sure. Got it. Sir, if you can hold up your microphone close to your mouth, it would be okay, I suppose.
Is it making difference? Hello? Hello? Is it better?
Yes, sir, it's
yeah, so I
better
think I will say like that. Yeah. So yeah, this current slide is showing the frequencies at which the various explosives respond. So on the left side, you have the upper line is showing terahertz, and the lower line is showing the wave number. Wave number is that 2 pi by lambda. So that wavelength. So you can see that for RDX, we have a peak at some about 0.8 or 0.67 terahertz. Then PTN. So all these various explosives, TNT and then HMX and all. These are explosives which are showing some particular peak. So if you have a terahertz source on radiation, and if you can measure the reflections at these frequencies, you can isolate the peak, and also you can know which kind of radiation is, which kind of explosive is being used. The other side, the right side, shows the terahertz through actually terahertz response for various textile materials. So normally, this is for this in the case of security application, one person can wear too many shirts over it, or many layers of textile on the body, and the explosives hidden inside. So knowing this response of this all various textile cloths, it is very easily detectable where anything is hiding behind this. So that is one interesting application to explore basically the explosives. So next slide, please. So that is the pictorial view about that person is having some explosive hidden inside, and you can find out. So there are other pictures which are in the shoes. Somebody has hidden some weapon, and on the right side there are some multiple layers. So you can actually see the layers, and also see something hidden in it. So these are the graphical or pictorial representation, and not actually images of the terahertz. So next slide, please. So this is the actual image by that same terahertz camera which I had shown, taken the human being is finding, and where he has hidden the guns. And some of the guns are plastic covered. It may not be metal. So you can easily distinguish. So these are actual image of the camera. Next slide, please. So this shows a dental investigation. Many times when we go for root canal or maybe for implantation, you take a dental X-ray. And this X-ray is the ionizing radiation. And many times the dentist wants to take multiple X-rays, but because of safety norms, you should not be exposed to too many times. And therefore, this you can see the inner part of the tooth, and you can make out what is where is the cavity and all that thing. So you can have a terahertz X-ray. Advantage is that it is not ionizing. So you get an advantage over the X-ray. So you can take multiple exposures, and you can do it. And what is the advantage? Other imaging technique, why they are not using? Because terahertz penetrates through the body, and also it has got a wavelength of the order of some 200 micron, 300 micron, and the features what we want to see, that is the cavity size and all, are much larger than 200 micron. So you can image it nicely. So on the other hand, if you go to microwave imaging, your wavelength is of the order of centimeters and few millimeters, where you can lose the focus. So terahertz had got a right frequency and less harmful, rather no harm to be used on human body. So that is one good application. Next slide. So this is another picture. So these are all different. So detecting cancerous tumor. There are, to detect cancer, there are very costly imaging system like PET scan and all, and they depend on the reaction of cancer, where you have to inject some chemicals and all that thing. Terahertz is like X-ray images, and you can detect the cancerous tumor. So this is another example. This is also an actual image. Next slide. So we will just see various applications, and then we'll come to the technology part. So this is in IC inside. When there is an integrated circuit, there is a chip which is shown in the red color, and the connections are taken out as shown in that like this. If this IC is healthy, you can test it without non-destructive testing. So these are the some of the examples. So very costly IC, if it is not easily done, it can be taken with a very handy camera, but terahertz, and you can make out whether there is an internal structural damage. It can also be used for quality control. Next slide, please. So we are seeing the taxonomy of the this leaf. So you can see leaves, and there the cell structure, rather the leaves. They are not called veins, but they are basically all that internal structure of a wheel. Yeah. leaf can be seen, and if that leaf has got sufficient water or not, that can be investigated. So whether when there is a controlled growth experiment, it is like that. So it has gone to next slide, and then let it be. So there is a graph on the right side which shows there is a difference for the water. So now next slide has already come. So there is a plating thickness kind of application. So many times, very precise engineering application, you need a plating thickness to be very controlled, and there is no other way. There are capacitance type of measurements which are not very accurate. So terahertz can give accurate plating thickness, because there again the wavelength is of the order of few microns, and the plating thickness are also in terms of microns. So a radiation which has got a wavelength in microns, which will work. So that there it shows clearly two peaks, and on any body you can see the plating thickness. You can measure the difference between two peaks, and time of flight you can simply calculate. So next one. Yeah, so he has come to the next one, and now then we will go to the now technology part. Okay, how? Okay, I have seen the terahertz technology, but how do I generate terahertz? See, I should be able to have a source. I should be able to have a detector, and then only I can be able to. I am able to do this experimentation. Now the problem with terahertz technology, it was called a terahertz gap. So why that gap is there? Because this that terahertz sources were not present. So now we will first look at the naturally available terahertz source. Here it just shows the calculation, which has got Planck's constant and Boltzmann constant. So with the temperature you can relate, and you will get the if the temperature is anything more than 10K, which is practically everywhere, and you can get a terahertz frequency. So it's a wide band depending on your molecular temperature and the molecular movements state. You will get the terahertz radiation available, and there are some terahertz radiation how it is detected. So I have given some big experiment. James Chadwick telescope and other telescopes have actually found or measured the terahertz radiation. But for us, even the theory is sufficient. With that temperature, you get a terahertz radiation available. But that is like illuminating the light is available. But I cannot do controlled terahertz radiation very easily. So there are simply cameras, because I have a free illumination like the terahertz radiation available, and I have to just make a detector. The camera which was seen earlier can be used. But when I have to interrogate, like for example, explosive detection, I need to make sources which are like radar or like a illuminating torch which is under my control. So that we will come and see. Next slide, please. Yeah. So in the next slide, we are giving yeah. So there are various ways by which you can do this radiation. So when you are talking about surface emission, so you have to create a ultra short pulse of a laser or optical pulse illumination, the first red portion. So it says ultra short pulse. What is ultra short? It is having a less than 100 femtosecond. Now you imagine it is difficult to have a microsecond pulse. Then it becomes much more difficult picosecond. So I am talking about 100 femtoseconds. So 100 femtosecond is 10 raised to minus 13. Femtosecond is 15, and 100 10 raised to minus 13 of a second. If you can generate pulse, this itself is a very difficult thing. But if you generate this, you are able to generate a terahertz radiation. Mathematically speaking, if you generate a laser frequency of a narrow pulse, and if it is a narrow pulse, you know that the other components are generated as a part of the sinc function, sin x by x, and you can pick out the terahertz. But we'll not go those many details at that level. But this is the technology, and that's why it was not easily possible to make it. The second one is photoconductive emission. There also you need to generate a 100 femtosecond pulse. So very narrow pulse generation is the key of terahertz generation. There are other aspects, but in this kind of terahertz generation using semiconductor or optical materials, then you need to generate a very narrow pulse. And that is the key technological part which was inhibiting for so many years. It was not possible to generate these terahertz sources simply because we could not generate a 100 femtosecond pulse. Next slide, please. So you have a picture. Now we are just talking how it is generated. So there is a gallium arsenide substrate and there is a deposition of metal uh, by vapor deposition or any sputtering and that kind of thing. So you have two electrodes which are shown in yellow, and that is a plus minus if I apply the voltage, and if it is a gallium nitride substrate. And if you put a less than 90 femtosecond, 100 femtosecond pulse, which is shown on the left of the screen, if in the gap where the voltage is present, the voltage difference is present, if you illuminate by a narrow pulse, you at the other side you get a terahertz. So that is a basically terahertz pulse generation. So that is how I generate terahertz. Now, if I can generate a pulse, you can see that you can look as a basically pulse radar. So you send a pulse, and by time of flight, you know the distances like thickness and explosive material and all. So I am able to generate this pulse. But now mind well, this is of the order of a fraction of milliwatt. So high power generation is still a problem, but a few milliwatt pulse at the terahertz generated by this method. Next slide, please. Now, after pulse generation, I have to create I have to direct that pulse because it's a point source. And as you know, and the antenna, a very point source will be able to, it will spread the radiation. It cannot, focus the beam. So you have to generate an antenna which will be focusing this terahertz radiation to the desired spot. If you have to illuminate the whole thing, it is possible. So this is one of the possible structures which is shown, which is a helical antenna on rather it is better to say a spiral antenna with some zigzag meander line at the input. So these are one of the research areas. If somebody is interested in research, this can do that. Only thing, fabricating these devices is only available at maybe 5-6 locations in India. So that is a limitation, but these are, one can think of these antennas. And if you illuminate this to the lower slide shows, this is a hemispherical antenna where that the other material is the hemisphere, and you make a PCB pattern on the bottom of this thing, and at the center of the bottom or the zigzag line, if you put two lasers with that frequency difference, and then you can generate, and that generated thing is by the lens antenna is directed. So that's why I have just seen the shown the how to pulse is generated, and then you have an antenna which will make it direct. So I have created a source which can be utilized for my practical purposes. And needless to say, the dimensions are a sub-millimeter or even a few micron on the pattern, and the whole hemisphere will be of the order of 4-5 millimeter. So it's a very tiny thing. And if you can generate, it has got a very interesting application. You can do spying with terahertz cameras also. Next slide. Yeah. So now after these devices, there is a high power. Now these devices will talk about only 100 microwatt, 1 milliwatt, maximum 1 milliwatt of power. So this puts a serious limitations. And hello. So this puts a serious limitations on the power. So there are other ways of generating power, which is vacuum devices. Now vacuum devices, as we have seen, the klystron and magnetron do not really go up to more than 10-20 megahertz. Then you have a backward wave oscillators which can generate a higher frequency radiation, but not really. It is very difficult to reach it at terahertz technology. So you have some backward wave oscillators. That is simply because the dimensions of the periodicity which we generate on the tube goes below sub-millimeters or millimeters, less than 0.1 millimeter, 0.2 millimeter, which is difficult to machine these objects. So backward wave oscillator and plastron or other classical devices are very difficult. There are people who have done some backward wave oscillator, or there are some other devices up to 400, 500 gigahertz, which is a state of art today. But you cannot generate. So these slow wave devices are, slow wave means this backward wave oscillator, slow wave devices, will not go into the detail, but there is a limitation of frequency. You can go a few fraction of terahertz. But there are fast wave devices like gyrotron. So gyrotron, this slide shows the picture of gyrotron, where you generate the microwave or the electromagnetic waves at higher frequency, and that being a fast wave device, it can have the periodicity of the repeatable structure slightly higher, manageable in few millimeters, because it's a fast wave device, and the phase velocity is higher than the velocity of light, but the group velocity is of course less. And you can generate terahertz by gyrotron, where you can talk about 100 milliwatt, sometimes watt or 2 watts also. So these devices are possible. They're very compact. You have to manage the heat properly, and the device's efficiency is of the order of 5%, 10%, 20% at most. So if you want to generate 1 kilowatt, you can see you have to burn 20 kilowatt in the small space. So there is a challenge, but it is possible. So this is a vacuum devices can generate high power, but it's a very costly option. But nevertheless, it is there. Next slide, please. Yeah, so this is a schematic of the gyrotron, and it shows the various parts, but we'll not go very much in detail. But you can see that yellow beam is the electron beam, which is focused by the magnetic coils, and it generates in a kind of a helical manner, and it is collected in the collector on the right side, which is a big copper structure where these electrons are terminated, they're impacted, and by the mirrors means a very smoothly surfaced this thing, you can generate a wave, which is the electromagnetic wave shown in red, which is available, that is terahertz. So it is not the electron. Electron will only have a velocity modulation, but electromagnetic waves can be taken out in the way it is shown, that is in gyrotron, and this is shown by the red light, red colored beam. And that is for that, but we will not go into detail. If somebody is interested, we can see this later. Next slide, please. So this is another picture of gyrotron, and again these were main where some people will be interested. So these are the internal structures of gyrotron, which will generate terahertz. So this is the only source which will make the terahertz radiation of in kilowatts or even in watts possible. So that therefore it is having a lot of significance, but nevertheless very costly, because the voltage between the collector and this anode cathode has to be around 80 kilovolts and all that thing. So you can imagine the complexity of technology. Next slide, please. Yeah. So this is a backward wave oscillator, just schematic again, or traveling wave tubes. These are slow wave structures, and these are again a vacuum device situation, where you have this anode, cathode, and collector. Cathode, then it gets heated, then collector, and ultimately
So your voice is not audible.
again. I don't know, because I'm holding the same position. So I will talk little
So,
loudly.
still not audible.
Now, hello.
I suppose your voice is very low.
So I have unmuted now. Is it okay?
So it's still low, sir.
Sir, I suggest please reconnect your microphone.
I am unmuting. Yeah.
Yeah, now it's fine, sir. Now it's fine.
I think it got muted by.
Yeah. Now it's fine.
Because this thing is there. Okay. So this slide, it's showing the this backward wave oscillator and traveling wave tube. That is again a structure which is very schematic, But in a backward wave oscillator, you inject RF and collect at the source end, that is where the electron beams are started. These are collectively, these are other options. So these are the vacuum devices which are capable of doing the basically generating terahertz. So these are the these are done by the CSF, this Thales and all. These are the companies which have released their schematic. This is not picture, but the earlier were the real pictures of the magnetron. That is all. Next slide, please. So now we have a table which shows what kind of device which can create over what frequency and up to what level. So you can see mainly that there is a very serious restriction on the power. No, sorry, the power is not given in the micro. Yeah, so it is giving the frequency, but there is a limitation of power which is of few watts. But which technology is useful for which frequency, and what is the frequency accuracy? Because when you have to do the scanning for the, let us say, explosives, you have to be accurate in frequency. So this is the table that gives a state of art technology. Next slide, please. So this is a general technological availability. So the x-axis is the frequency and the y-axis is the power. And you can see the terahertz frequency, there is a dip. It is inside, it is lower, and you are talking about only 1 watt of power, because higher power things are not available. So there are various technologies which is possible. And the gyrotron you can see at the lower terahertz, but at blue side up there. And you can talk about some 10 watts of power, 10, 20, 50 watts. But you can see that high power is not possible. And then there are laser kind of sources which are talking about 0.01 watt, that is only 10 milliwatt. So we suddenly dropped to 10 milliwatts, and all the semiconductor sources are 10 milliwatts or lower. So we have seen that available technologies and the technological limitations of generation of terahertz. Next slide, please. Now this slide has got a lot of text, but it is essentially saying that photoconductive sampling and other sources, the electro-optical sampling, which are essentially shining lasers. I'm not going to read because it will be boring. So electro-optic sampling or photoconducting sampling, where you put a laser, and due to the down conversion or the sharp layer, the harmonics, you can pick up the terahertz. So these are the other sources of terahertz. So since it is only text, the slide is not very interesting. Next slide, please. Now we will come to the detection. I'm sorry. Please go to the previous slide. I made a mistake. Previous slide, please. No, the next. Yeah, so this slide was actually for the detection and not for the source. So I made a mistake. So we have generated the source. Now, when the terahertz radiation is falling, we need a detector. Because either it is a reflective or the transmittive. So whenever it passes through the sample or it gets reflected, I should be able to detect it, so that I will be able to find some inference whether it is attenuation. So this is for the detection. So photoconductive sampling, you actually generate the process is reverse. When you put a laser, you get a terahertz out. When you put a terahertz, you have to shine a laser there, and you have to like a mixing again and get the terahertz power. So that is photoconductive mixing. And electro-optic is a similar case. That is where you apply a bias on a gallium arsenide chip, where the same antenna is used to focus the terahertz radiation. When the terahertz radiation falls on it, I shine laser simultaneously. Laser is shining. So by mixing, you get a laser out. It is like down conversion in the mixer while generating, and up conversion while the receiving, because you can detect it. Laser technology is very well established in detection and transmission. So laser plus terahertz will have a slight frequency shift in the laser, and I make the laser power. measure the laser power. So that is a way of detection. Now next slide, please. So what was a earlier detection was called synchronous detection, because that time the laser has to be present. Now there are other ways of detection, which is the asynchronous detection. Then that means I don't have to make the laser present at that time. So because that, for that the synchronous detection has got a disadvantage, because I exactly should know when the terahertz radiation is falling on me. So that is the time of flight calculations. So it requires a lot of controlled application where you can detect. So this is where both the transmitter, receiver, and the object is in my control. For example, I put a sample where there are explosives or where there are some hazardous material. So the sample is in my control, the source is in my control. So that time you do synchronous detection. But asynchronous detection, where you just have to see the as a camera or the person is walking. So there are the asynchronous detection, which you can shine terahertz light on by some source, and the detection could be without the presence of laser. So the best is a very popular one is the bolometer. Bolometer is a device which basically generates the energy. Now for microwave detectors also there is a bolometer. Rise is measure, and today our existing technology can allow you to measure the temperature rise of the order of millikelvin, rather 1,000th of a milligrade, and therefore by proper design you can get bolometers. The commercial cameras which were shown, which are easily available today, are having the bolometer. This kind of technology. So very micro bolometer and a very small micron level spots are created, and each spot the temperature rise is measured individually. So this array works like a camera film, and you are able to generate the bolometer. So next slide, please. So the pulse terahertz imaging, you can, this is one schematic where you can show a structure. Now we have seen how to do the pulse and how you can pulse generation. We have seen how to make antenna to focus, and we have seen the detectors, both synchronous and asynchronous. So we are just revisiting the application. So we have seen the application as a user. Now we are going to see the application as a technologist. How exactly to form the experiment or how the application. So this shows the either coating thickness or internal structures. So I can shine a terahertz pulse and I can get various reflections from different pulses. So I can have a slant pulse and I get the thing out. So this is how I actually form the equation. Earlier we have just seen the pictures. Now this is a internal picture or schematic of the experimentation. So this is one for the thickness measurements of various levels, either coating thickness or some micro biological structure or something. So and any other semiconductor structure also, because these dimensions are a fraction of micron, and I have a frequency wavelength which is another one. So that is one side. Next slide, please. So this is also a time domain spectroscopy. So in when you now we have seen there is a little bit of limitation. So when you have a normal microspectrum analyzer, that spectrum analyzer is able to sweep all the frequency and I get a response. But in terahertz, we have seen we are generating frequency with a very much difficulty. And after that, due to that difficulty, I can generate only terahertz at very limited source frequencies. And then how do I generate suppose I want to see the complete, for example, TNT as the explosive TNT is detected at 700 gigahertz, but I don't have a source at 700 gigahertz. So what do I do? So therefore, the time domain spectroscopy technique has come, which I can generate a very narrow pulse, again 100 femtosecond, sometimes 10 femtosecond pulse at, let us say, 1.4 terahertz. And with that 10 femtosecond, so if you see at the pulse response, so it will generate multiple frequency. Sin x by x 1 upon 10 femtosecond will generate a terahertz frequencies and multiple terahertz frequency bands, and it will illuminate. So it is this source with a narrow pulse is equivalent to multiple frequency sources, and whether if that particular element, let us say some explosive or some biological substance is available, it will respond to that. So instead of a frequency sweep, it is possible to generate a multi-frequency source by narrow pulse. So this is that application, and you can see the blue thing is a terahertz spectrum, and you can see it is wide. Now, okay, if I have generated, but how do I take it? So I have a filter, very narrow filter. It's possible in terahertz, so I can see the response at a particular frequency selectively. But the problem was to generating source, and this source can be generated wideband by narrow pulse. So this is the slide which illustrates this kind of concept. Next slide, please. This is actually a block diagram. When you want to do it specifically a Terahertz system, building up system. So it is even today, the easy systems are by lasers, because laser generation is easy. So you have a pulse laser, and that we can see on the left side, the top side, and then you have to generate optics. That is, there is a beam splitter. Huh? It is concept like a basically this radar. So this is there is a beam splitter. That means I am taking out another one part of the beam outside, and the other part is for the detection. So it is like a taking local oscillator out. So I transmit with one beam and the other this thing. So that there is a time delayed probe beam. So that probe beam is the same part of the beam which is delayed in time. And now I have used the upper part, the terahertz excitation beam, that falls on the terahertz emitter. That means it is some electro-optic crystal or something which will generate terahertz. And now that terahertz falls on the sample, and the probe beam I can delay. So I can see whether that terahertz response has come with a control delay, because that timer delay is in my control. So if I do it 1 nanosecond, half nanosecond, fraction of a nanosecond, and with that small sometimes femtosecond delays, and by that delay I exactly know where the signal has come, and that is a system which will take output 1, output 2. So output 1 is the terahertz source, rather it is a trigger, and output the other lock-in outputs are basically taken synchronously, and the system measures the delay, and hence the amplitude where it comes higher at what delay will determine the physical distance in the terahertz. So these are the system details. When you have to build up the system, these are some of the popular configurations and which are possible technologically. So one has to select the configuration which is required for the our application. So there are some different sources and different configurations where essentially you have a terahertz pulses, and that will generate different terahertz, and which you can see like in radars you have the mixer down converters. Here you have optical components, various mirrors, various generators. So it is a optics which is in the laser, not in terahertz band, and you generate terahertz whenever it is required, which is shown in a blue slide. Next slide, please. Yeah, so this is another, there are various components, system details, which are specific to certain systems. So I am showing various options, but these are technologically complex and it can be discussed only in the context of particular thing. For example, lower left-hand corner, I have shown the lens design. So it is a dielectric hemisphere, and when I terahertz is generated, I can create a beam. So this is the silicon lens or some dielectric materials of various. On the right lower side, we have a different mirrors, which are the parabolic mirrors and which can direct the beam. And these are the terahertz beam maneuvering. The blue color is for the terahertz and red color is for the laser. So you generate a laser beam from the lower side, and that hemisphere creates terahertz, and it is taken to the sample, and it can be scanned, it can be focused. All that is the optic techniques which are very well established. Optical mirrors for the terahertz is essentially very nicely polished. The surface correctness is within a micron. So that kind of instrumentation is possible. So these are all existing instrumentation in the world. So this kind of generation can be done. Next slide, please. This is next things. This is another picture which is again having same. So you have top right hand corner, you have some CO2 pump lasers and all. So these lasers are available. So now with a laser availability of laser and with good optics, I can generate a Terahertz testing platform, investigating platforms, and these are specific examples. And this may not be a right place to detail every block diagram, but this is a possibility, and these technologies are existing in the world. So with this facility one can do very good research, and if you have a facility you can put a very different samples. So unexplored area is a biological samples and very non-metal cement material and all. These are yet to be explored and the characterized. So characterization of various material is a problem, and it is done with this kind of systems. Next slide. So these are certain images, and it is shown with the image, how the details are there. So the top left is 2.2 terahertz, very high terahertz. You can see the high focusing because the wavelength is 0.118 micron. And as the wavelength increases and lower terahertz frequency there, you can see the same object with a lesser. It is like defocusing. So if you have a right frequency, right wavelength, you can do right focusing, and it depends on the feature dimension which you want to see. So when you want to see zero point 0.1 micron, zero point 0.1 millimeter, you have this kind of accuracy. So this is the example which shows the various, and the upper side is a transmission terahertz measurement, other is a reflection. So when you have to see the higher one with actually to the terahertz, you have a transmission slide on the upper side. So this is an example actual photographs. Next. So now you have a simple camera. These are some experimentation. There's some same pictures which are shown. You can see the plastic gun which is also seen, because nowadays people are having weapons in the plastic, and instead of firing bullets they fire some small needles or some hazardous chemicals. So for this new weaponry, new investigation techniques are possible. These are again real image from company called INO Canada, and TerraSense INO. These are one of the leading companies which are equipments are available in India. Some equipments are not available in India for the security reasons. So these are some pictures. Next. Now this is again, we come back to our camera, which is easily available, very compact camera, just some specification. This is not advertisement, but this is easily possible, available. So we can right away buy camera, but other systems you have to build up, or even the vacuum devices you have to build up. So this comes to the end of my talk, and I would like be happy to answer some questions. Thank you. Next slide, which is a thank you slide. So I have
thank you, sir,
completed.
for the session. We got a couple of questions from.
Yes, please.
First will be the first question is terahertz you mentioned is a penetrating wave technology. So won't it be harmful for the local tissues? Does it produce
that is what exactly
in local tissues?
Yes, that is what exactly I mean. It penetrates when the radiation goes in, but it is non-ionizing, so it is not harmful. And we are generally talking about milliwatt of power. See, you have the other harmful, like for example, the lower frequency still penetrates, and micro radiation is, almost proven to be harmful. So anything on the higher side, higher watts, is harmful. So there are thermal and non-thermal effect for non-ionizing radiation, but terahertz we are talking about milliwatt power, so it is not harmful at all. Rather, it's a cell phone technology. You are talking about 2-3 watts near your ear, so it is a long-term harmful. So in the terahertz side, we are non-ionizing and we are much lesser power, so it's not harmful at all, and that's why it has got a lot of interest.
Okay, thank you, sir. I guess that query was clear. The next question is, if does terahertz technology damage DNA? And if it does so, can it be used for treatment of diseases like COVID?
No. So this does not damage DNA, because again it is a harmless. We are saying it is only for the investigative or management person. For the COVID, this is not terahertz, but what is the information? So the damaging, of course, your higher radiations are there, gamma rays and other things. But what is possible is called a far infrared radiation, which is the higher frequency where wavelength is about 200 nanometers. The terahertz we are talking about in fraction of micrometer, so nothing to do with terahertz. But since the question is asked, see, in ultraviolet region, we have ultraviolet A, B, and C. So far ultraviolet is, harmful. Rather, it can kill the bacteria. And far ultraviolet C is less than 200 nanometer wavelength. So those people can kill, but they also, so when you want to just disinfect this far infrared C band, that means the less than 200 nanometer is easily used. But sometimes people want to use for a biological age, so they have created some small band which is called far infrared, but not harmful. So it is 207 to 220 nanometer wavelength. So that ultraviolet is used, but the sources are very costly and very not so easily available. But that is a challenge, and COVID and all other bacteria can be killed without harming, not strongly harming human, which is 207 to 220. And less than 200 it kills, but it also harms the human skin. So from there that ionizing part starts, and so in UH. But terahertz is anyway safe, but it is also not useful for killing. It is useful for watching. Okay. Any other questions?
Okay, thank you, sir. Yeah, one more. One question was, why do we specifically use gallium arsenide for generation of terahertz signal?
No. See, this you can generate anything, but this gallium arsenide is this 3,5 compound. That is the group 3 and group 5. So there you can form this. You can make the electron jump into various levels, and your terahertz. Basically, terahertz radiation is a generated by, it is a mixer-like structure in our RF and microwave. So you need a non-linearity where you can jump with a lesser power. So when you shine laser, all group 3, group 5 compound are good. So indium something, all group 3 of atomic table, gallium arsenide is most popular, and we have in semiconductor physics that is available technology. But actually in terahertz, there are many materials are used. In some of my slides it was there, but it would have been unnecessary. Beryllium and then indium and various things are there. But gallium is masta hai. So normal deviations, normal generation gallium arsenide is economical also, and it has got that basically 3 group and 5 group compounds, which that electron can jump easily. If you have 2-1 group, electron is very nicely bounded to your atom. So near 4 is a pure semiconductor, so you have to make it, doping and all is possible, so you can create semiconductor non-linearities. So that's why gallium arsenide. Yes.
Okay, thank you, sir. If any other participants have other queries, please feel free to ask in the chat section. Sir is available currently.
I can see 30 chats, but basically somebody would.
Any other queries?
Nice session is okay, but if some specific queries, you can of course email afterwards. That is one part, but you can ask if somebody reads it, because there are some 30 chats, but many of them are hello kind of thing. So if there is specific query, I would like to answer. Otherwise, thank you very much for your presence and listening.
Okay, thank you, sir, for your deep insights in terahertz technology and its applications. Your information was indeed valuable, and surely, I guess, it would inspire some or many of us to take up new opportunities and challenges in this emerging trend. Thank you once again for accepting our invite and sharing your knowledge with us.
Yeah, thank you. I also enjoyed the company, but this virtual thing is not very real. But no problem. In this scenario, we can use that only. Thank you very much, and it was really pleasure. Thank you. Shall I leave the meeting? Yeah.
So 1 minute. It was a really informative session. I would ask Gonge sir to speak few words. Dr. Gonge.
Yeah, of course. Yeah.
Sir, thank
So I am one among you, so don't have to be very formal,
in
sir.
your busy schedule, sir, you are given time. I know your schedule. So
Yes.
thanks, sir, for your this information and new information you have shared with us, sir. Very thanks, sir. I know you are always with us. St. John.
No. I know you are the
Same.
Gonge sir was our co-researcher, so we have.
Principal and management, I am very thankful to you, sir.
Right.
Thank you.
Thank you very much.
Thank you, Dr. Kushal sir, Vinay sir, Gonge sir, all the team coordinators. Thank you, all the participants. I would like to ask all the participants to just turn on their video for a few seconds. We will have a photograph.
You can take a photograph. Huh?
Yes, sir. Turn on your video, please, for a few seconds. Yes, done.
Did you have a screenshot?
Okay, thank you.
Yes.
Yes.
Yes, I have taken the
Okay.
photo.
Okay.
Very good.
Okay.
Thank you, sir. I would like to thank you and
Yes,
all the
it was-
participants.
Thank
Yes,
you, sir. Sakla sir, thank you.
Thank you. Namaste. Good. Thank you very much. Chalo, I am leaving the meeting, right? Thank you.
Yes, sir.
Okay.
Okay,
Sure,
thank you.
sure.
Thank you very much.
Yes, sir.
Guys, our next session will begin at 11:45, exactly 10 minutes from now.
Everyone, please stay tuned. Next speaker will be joining. Dhananjay, sir, can we see you? Sir has already joined.
Yeah, definitely. Can you see me?
Yes, sir.
Yeah. Very good morning to all of you.
Yes,
Good morning,
sir.
sir.
Yeah. Hi. Hello, Dr. Gonge.
Hi.
Nice to see you.
It's a glad you are with me.
Thank you. So maybe I guess we can take a quick break because it was 1 hour session and then I guess we can start then.